we have twists of Burkhardt quartic threefolds, and the talk is given by Nils. Oh,
okay.
So is it okay if we record?
Yes, yeah, that's fine.
Yeah.
I don't see the recording starting yet. Oh.
It says pause/stop recording for me, so I guess it's recording.
Okay.
Okay.
Okay. Well, welcome, thanks for sticking around. I'm very happy that ANS is once again happening. I'm a little bit sad that I have to attend remotely, but traveling transatlantically at the moment is a bit of a challenge. Okay, I'll be talking about twists of quartic threefolds, and part of this is work that is based on the master's thesis of my co-author, Eugene Filatov, who is currently affiliated with the University of Toronto. Okay, so I'll quickly talk about sort of the perspective of this. So the Burkhardt quartic is a very classical object. It was studied by Klein and his students, Burkhardt and Maschke, around 1890. It's a threefold that happens to be rational, although that almost seems to be a little bit of an accident. What is much more meaningful for the interpretation of the object is that it's unirational. So there is a finite degree rational map from, well, P3 to the threefold. However, this is not the case for all its twists over Q, as was proven by Caligari and Chidambara. And the Burkhardt quartic has already received a little bit of attention in previous answers, particularly the previous one, at 14 in 2020. And today I'll be looking at an interesting connection about these rationality questions with the field of definition obstructions that exist for genus 2 curves. We'll see what that actually is. We'll see a very satisfying explanation of this in terms of the representation theory of SP4F3. This will have some surprising consequences for the existence of rational points on these twists of Burkhardt quartics, and that leads to a tantalizing question at the end, so stick around. Okay, so the Burkhardt quartic threefold has a very explicit equation. It's an equation in 5 variables, homogeneous of degree 4, so that gives you a hypersurface of degree 4 in P4. It can be characterized in several ways. One good one is that it has 45 nodal singularities. That's the maximum that a quartic threefold. Oh, was there a question? No. Okay. It has 45 nodal singularities, and that's the maximum that a quartic threefold in P4 can have. And in fact, it is the case that any quartic threefold that has that many nodes is in fact projectively equivalent to the Burkhardt, at least over an algebraically closed field. Its automorphism group is this huge group, the simple group of order 25,920. And there's a special locus on the Burkhardt, which consists of, well, the vanishing of the Hessian. If you intersect that locus with the Burkhardt itself, you get a union of 40 planes. These are called the J-planes. They play an important role in various interpretations of the Burkhardt quartic. In particular, if you take a point in the complement of the Hessian, then you can naturally construct a Kummer quartic surface from that point. And you can actually find a genus 2 curve such that the Jacobian of that curve is has that Kummer surface, and furthermore that Jacobian has a prescribed 3 torsion structure. That's basically the reason why there's this big automorphism group here. If you look at what happens actually, is that you can construct the projective dual of this surface, which has on it a plane conic that passes through 6 of the nodes of that Kummer quartic surface. So if we now move to twists of the Burkhardt quartic, so those are threefolds that over a separable closure are isomorphic to this reference Burkhardt quartic, we find that, well, those twists are classified by Gowell cohomology. So the first cohomology taking values in this PSP 4F3 that classifies the twists. And the moduli interpretation largely goes through. We can still construct these dual Kummer quartic surfaces with a conic on it that passes through 6 nodes. But this is where the obstruction comes in. If you specify on a conic 6 points, you can do that by intersecting with a cubic curve, for instance, then that specifies basically, well, 6 points on the genus 0 curve. So that would be the branch locus of a genus 2 curve, you would normally think. But in order to actually realize a double cover with that ramification locus, you're gonna need a rational point on the conic. If there's no rational point on the conic, then your moduli do exist over your base field, but you can't actually realize this moduli interpretation over the ground field in those cases, if you insist on doing that with a genus 2 curve. You can see where the problem is sort of coming from, and that is coming from the fact that you're only specifying this curve up to quadratic twist. So we get an obstruction map, and this generally consists of moduli spaces of genus 2 curves, where for your point, you can assign to it the class of this conic. The isomorphism class of that conic gives you an element in the Brouwer group of your base field, and only if that is trivial do you have a rational point on your conic, and hence can you realize your moduli. So looking a little bit more carefully at how that pans out for the Burkhardt. So what we've basically seen is that the Burkhardt is birational to M23, which is basically the genus 2 equivalent of the modular curve X3. So that's it's a moduli space with full 3-level structure. So you're specifying the structure of the 3 torsion. Now, if you look at the automorphism groups that play a role there, the pairing preserving automorphisms, there's a Y pairing on the 3 torsion. The pairing preserving automorphisms have form a group SP4F3, and the automorphism group that we found for the Burkhardt is actually a quotient of that by the center. So if you take Galois cohomology of that sequence, if you give yourself a cocycle taking values in PSP4, then you have a map to the Brouwer group. It's basically, I mean, we call it again an obstruction map, and only if that is trivial can you lift your twist to something that actually corresponds to F3 or to SP4. So you can actually check that this works out completely well, that really the obstruction map that you're finding is a function of the twist and not of a rational point on it. So if you can find a rational point and evaluate your obstruction map there, you will just always get the same class of a conic. So that leads to a question, though. How do you compute this obstruction directly from the twist without having to appeal to a rational point? Because it's not clear that those are always there, for instance. So that turns out to have a fairly satisfactory explanation in terms of the representation theory of SP4F3. So for that, we need to refer back to the unirational parametrization that Burkhardt admits, as I alluded to before. It's a degree 6 map, and it corresponds to choosing a Weierstrass point, so an odd theta characteristic, on the supposed genus 2 curve that's around. And there's a very good representation theoretic explanation of where that map comes from, and it has to do with the fact that SP4F3 has an irreducible module with a faithful action on it of dimension 4, And if we take the fourth symmetric power of that, so that's basically degree 4 polynomials in whatever the coordinates are on the space over here, on that V4, then it decomposes in a 5-dimensional and a 30-dimensional representation. And if you take produce of that, then, well, this here is a 5-dimensional space of degree 4 forms on basically P3. So that gives you a map to from P3 to P4, and you can check that the image of that is in fact exactly the Burkhardt. So you can find this unidirectional parameterization right in the representation theory of the of SP4F3. Now, if we twist, there might be a problem because we're interested in twisting with values in the projective group. So we have to deal with non-trivial obstructions as well. And that V4 here only exists if you can actually lift your twist to 1, taking values in SP4F3. But we can go halfway in our symmetric powers. If we just take the symmetric square of V4, we get a module V10. And the scalars will now act by squares on that. So the center, which acts by -1, now acts trivially. So these representations that we're getting here, this V10, will actually be just a PSP for F3 module. And in fact, we can recover it from V5, that's basically the space in which the Burkhardt lives, directly because it also arises as the alternating square dual of the V5. You can check that those are the same. These are fairly straightforward character computations. Well, there are some chats here. Is that important for me? Oh, sorry. Okay, that's not going to work. Okay, so the second symmetric square gives us this 10-dimensional space, and if we take its symmetric square, we're obviously going to recover everything that we got from the fourth symmetric square of V4 originally, but we get a little bit of extra as well. We get this V20, and if you look at what that is basically the locus of, those are basically the quadratic equations that define the locus of the second Veronese embedding. So we can actually recover from all of this data without having to have a V4, a threefold in P9 that admits a map given by quadratics on that threefold in P9 that again have as image the corresponding Burkhardt. And this now doesn't need our obstruction to be trivial. However, if the obstruction is trivial, then this M will simply be the second Veronese embedding of P3, and then the map that we have over here reduces again to the original unidirectional parametrization that we had. Now, it's a theorem here that the obstruction is now represented by the class of this M here, which is indeed a variety. As you can see, that over an algebraically closed field will be isomorphic to P3. So that's a Brouwer-Severi variety, which means that its isomorphism class is again given by an element in the Brouwer group. Okay, so that gives a very satisfactory explanation of where the unidirectional parametrization is coming from and how you can recognize this obstruction from just the twist and its geometry directly. You don't need, it leads to Galois homology, but you get geometric objects catching everything that you would like. But this has some consequences for rational points, and this has to do with the period and index of elements in the Brouwer group. So if you're looking at two torsion in the Brouwer group, then a class there can be represented by a conic exactly when its index is at most 2. So its index is 1 or 2. But it's not necessarily the case that any two torsion element in the Brouwer group in fact has index 2. It can have a larger index as well. And that has interesting consequences. So here we have a bunch of results now that relate properties of rational points to whether the obstruction is trivial or not. So if you have trivial obstruction, then your variety is unirational. So you have plenty of rational points. There's a risky dense. There's an extra result here that if the Hessian has a k-rational J-plane, then in fact the obstruction must be trivial, because having a J-plane available allows you to construct this curve C alpha as the discriminant of a cubic genus 1 cover of a P1. And in that case, your genus 2 curve just arises without obstruction. You just explicitly construct the curve, and hence the obstruction must be trivial in those cases. And then in the last step here, if the index is in fact larger than 2, then that would mean that your Burkhardt has only singular points. The argument for that is also fairly straightforward. Any point outside of the Hessian would lead to a point that has an appropriate moduli interpretation, and hence you would be able to construct a conic that would have to represent the Brouwer class, and hence you get a Brouwer class that's represented by a conic, and hence of index at most 2. And furthermore, you see that if your index is larger than 2, then no quadratic extension will kill your obstruction, which means by this step 2 here that no J-plane can be defined over a quadratic extension. The J-planes all must form larger Galois orbits, which means that if you have a point that lies in the Hessian locus, it would have to, and that is rational, Galois stable, it would need to lie on at least 3 J-planes, and only the singularities do that. So having index larger than 2 here puts severe restrictions on the rational points that would be able to exist on such a twist of the Burkhardt. Now, that might all be vacuous if that never happens. So let's look at some examples. Let's look that we can indeed realize index 1, 2, and 4. So for trivial obstruction, we have our reference Burkhardt. For index 2, there's another very classical model of the Burkhardt. If you take the first and second elementary symmetric polynomials and take their vanishing locus in 6 variables, then you get a quartic variety that lies in a hypersurface. So indeed, it is a quartic surface in P4 again, or quartic threefold, sorry. And you can compute that its obstruction is represented by the quaternion algebra -1, -3, and that's non-trivial over Q. So that's an example, at least over Q, basically over any field where that algebra is non-trivial. And for index 4, we have to work a little bit harder, and that's because over local and global fields, the period actually must equal the index for the Brouwer group. That's a rather deep theorem for global fields. So we have to step up to another kind of field, and here a bivariate function field over a non-algebraically closed field like R does the job. And with a little bit of careful twisting, we can construct a twist here that has an obstruction that is represented by a tensor product of 2 quaternion algebras. And you can check that that is not a class that can be represented by any single quaternion algebra. So that means it has to be of index 4. So this leads to an interesting observation, perhaps, and that is that B double prime here is an example of a moduli space that's geometrically rational. That's still the case. It's a Burkhardt. And yet has no rational points, certainly not in the locus that's sort of not in the boundary of its moduli interpretation. But in fact, if you blow up the singularities, you wouldn't be able to have rational points there either. So it shows that certain a priori admissible level structures on Kummer quartics do not actually occur over RST. And that's just because, well, I mean, it ends up being measured by the fact that you have this obstruction of index 4. So conversely, on our index 2 example, we can actually prove that we do have Zariski density of the rational points there. but we don't have a nice unirational parametrization available to prove that. However, you can find relatively easily many elliptic fibrations on this surface. One way, for instance, is the singular locus is highly non-general, and for B prime, it actually has 15 rational points lying in it, and they have a lot of collinearities between them. And then if you take linear spaces that contain a line that contains 3 of these singularities, then it ends up intersecting your Burkhardt basically in that line together with a plane cubic. So you get loads of plane cubics on this that go through singularities as well. So they have rational, that you can use that to force rational points on them. So they are elliptic curves. And now there's a standard trick if you have loads of fibrations or elliptic fibrations to get loads of rational points on your surfaces as well. And the idea is first you try and find one of those elliptic curves that has positive rank. So then you can find loads of rational points at least on that curve. Now, if you take another fibration that's transversal to this elliptic curve, you can take all the fibers that pass through those rational points. So that's going to give you a two-dimensional, that's going to give you something that's dense in a two-dimensional subvariety. Because you forced an extra point on these curves, these tend to have loads of rational points themselves again. And now you fill out rational points on a two-dimensional subspace. If you do this one more time with a fibration that's transversal again to this one, you can stretch up your rational points to be Zariski dense in your entire variety. So with that argument, you can indeed prove that the rational points on B prime are Zariski dense. And that then leads to a question. So we have some observations here. If the obstruction is trivial, then your Burkhardt is unirational, so its rational points are Zariski dense. If the index is 4, then the rational points are definitely not Zariski dense. And if the index is 2, we have at least one example where we do have Zariski density of rational points. So the question that I would like to end with now is it the case that if the index is at most 2, that rational points must lie Zariski dense on twists of Burkhardts? This would actually imply that all Burkhardt quartics over Q would have Zariski dense rational points. So I thank you for your attention, and I'll leave it at that, and I'm happy to take questions.